Hello and welcome to today's video. In this video, we're going to look at an application once again, and this time it's an application from economics. Specifically, we're going to talk about the Gini index. So the title of this section is Application the Gini index. Now, the general idea of what we are going to discuss is to find a measure of income or wealth equality or inequality in a society. So the question is, how fair is a society in terms of income or in terms of wealth distribution? So this is the general goal of the following. Find a measure of income or of wealth inequality. And this measure is going to be what we call the Gini index. That is based on the idea of the Lorenz curve. So we'll first have to discuss the Lorenz curve. Lorenz curve is usually denoted by L. And this Lorenz curve is the curve defined on the interval from 0 to 1 that maps to the interval from 0 to 1. And it's defined in the following way. L of x is the proportion of wealth of a society that is held by the bottom x of the population. So L of 10, for example, or L of 0.1, L of 10%, is the proportion of wealth that is held by the bottom 10% of the society. L of 90% would be the proportion of wealth of that society that is held by the bottom 90%. Or conversely, the proportion of wealth that is not held by the top 10%. Okay, so that's the definition of the Lorenz curve. So this is the proportion of wealth of a society or of income earned in a society that is held by the bottom x of the population. So imagine the population is sorted by wealth or by income, and then at x, at 10%, 20%, 50%, we just make a cut, and we sum up the wealth up to this point. That is L of x. So naturally, a few properties of the curve. L of 0, of course, will be 0, right? The bottom 0% hold nothing, so L of 0 is 0. And L of 1 is 1. The bottom 100% is all of the population, and of course, the total population, holds all wealth of that society. So, in a society with perfect equity, we would have L of x equals x. Everyone has the same income or the same wealth. So, the wealth held by the bottom x increases steadily with x, and it increases linearly. So that would mean the situation L of x equals x corresponds to perfect equity. So that means everyone has the same wealth. And that curve, L of x equals x, is also referred to as the ideal curve for that reason. That is kind of the perfect society. And that means usually in real societies, L of x will be somewhere below that curve x. And the question is, how far below is L of x? And that question is used to define the Gini index, and that is just one number that measures kind of how far below the ideal curve the real Lorentz curve is. So let's get to the Gini index. That's denoted by G. And J is defined as the fraction of the area between the ideal curve and the real Lorentz curve to the area between the ideal curve and the x-axis. So let's write that down first, and then I'll show you how the definition works with the sketch. So G is the fraction of the area between ideal curve and actual Lorentz curve to the area between ideal curve and x-axis. So if you want to make a quick sketch of that situation, let's say work like this. So let's say here we have top 5, here's 1, same thing here, top 5, here's 1. So the ideal Lorentz curve, all Lorentz curves start at 0, all Lorentz curves end at this point 1, 1. The ideal Lorentz curve is then this here. Yeah, so that is the ideal curve. Let's say the real curve that lies somewhere below that, and the real curve also starts at 0 and ends at this point here, 1, 1, and is somewhere below that curve. So that could look like this, for example. And that is the actual Lorentz curve. Then the Gini index measures the size of this area here relative to that area. So G is defined as the orange area divided by the pink area. That's the Gini index. And as I said, with perfect equity, we have the ideal Lorentz curve, so then the orange area is 0, and that means the Gini index becomes 0. For maximum inequity, we have a Lorentz curve that looks like this here, so nobody has anything apart from one person owns all the wealth, so that is kind of the worst Lorentz curve that we could have in terms of equity, and then the Gini index would be 1. Okay, so the Gini index is between 0 and 1. The situation G equals 0 corresponds to perfect equity. So that means the Lorentz curve here is the ideal curve. The situation G equals 1 is maximum inequity. Basically, that means one person owns everything. And just to give you an idea of the real Gini index, usually there's two measures. You could take the Gini index by income, or you could look at the wealth distribution. If you look at the Gini index by income, then typical values start at about 23%. So you have about 0.23. Data is from just a few years ago usually. At that time, Slovenia had the lowest Gini index. So that's the closest you could get to perfect equity. Germany is around 0.31. About 30%. For comparison, the United States are around 42. And the worst I could find is 0.63. More than twice the value of Germany. That is for South Africa. Now, if you look at the Gini index by wealth, things look different. So you could imagine if the income is not equally distributed, then of course, over the years, the wealth accumulates in a very different way for different parts of the population. So you would expect the Gini index by wealth to be higher than that by income, generally speaking. And it is by quite some amount. The lowest I could find was 50%. That is true for Slovakia. Germany is at about 82%. The USA is pretty close, just for reference, 85%. And the worst I could find, 90%, surprisingly for me, the Netherlands. Okay, so that much about the application itself. Now, what does that all have to do with integration, you will ask, and or know already from the definition? Of course, here is the connection to integration. What we need to do to compute the Gini index is we need to compute this area here. That's a classical integral. And we need to compute this area. Now, that is really an integral because we need to take into account this Lorentz curve. And that is usually measured empirically. So you have something like a piecewise definition here with lots and lots of pieces. But given that Lorentz curve, we could compute the Gini index using an integral. And here's how we have to do that. So how do we compute the Gini index? So by definition, the Gini index is the integral between 0 and 1 of the area between that curve, the ideal curve, defined by L of x equals x, and the actual curve L of x. So we take the difference, x minus L of x dx, integrate that from 0 to 1. And then we divide that by the area below the ideal curve. So the integral over just x dx. Now, if you want to compute that, we can, of course, just split up this integral up here. So that's the integral over x dx minus the 1 over L of x dx. And here we also have the integral over x dx. And that one we can compute. That is x squared over 2 from 0 to 1. Same here. X squared over 2 from 0 to 1 minus this integral from 0 to 1 over L of x dx. And of course, we will not get rid of that part here unless we know L of x explicitly. So in this general formula, L of x will just remain there and the integral will just remain there. So what do we get? Well, here we can take this fraction apart into two parts. The first part is this expression over this expression, so that is 1. And then we have this integral L of x dx divided by that expression here, when that is 1/2 minus 0. So what do we get in the end? Well, we get 1 minus, and 1 over 1/2 is 2. So 1 minus 2 times the integral over L of x dx. So this is a general formula once you know the Lorentz curve. And if you make some assumptions on the Lorentz curve, or if you have an empirical description, for example, as a piecewise function of the Lorentz curve, then you can compute this integral, and that will then give you the Gini index. So that was an example of an application of integration in the economic sciences, which I hope you found interesting. We'll continue with integration techniques and some more general ideas about integration in the upcoming videos. And as usual, I hope I'll see you then.